Let's start. Yesterday, we have looked into how can we determine stability using Bode plot. A system is stable if at the phase minus 180 degrees, the magnitude is negative, less than 0 dB. So if we can ensure that, then the system is stable. Today, we will look into another two important quantitative measures in Bode plot, which is called gain margin and also phase margin. We have gain margin, phase margin, and they are also related to stability. We'll see later. System with high gain in phase margin will have higher chances in the system, can have, we call it more stable. Okay? So the gain, it will be, the range of K will be higher if the system has gain and higher gain and phase margin. So this is the definition for gain margin. Gain margin, we normally denote by GM, gain margin, is the change required in open loop gain at minus 180 degrees. Again, we look at minus 180 degrees, and we will see gain at that frequency. That frequency is called gain margin frequency, omega GM. Omega GM is when the phase minus 180 degrees. Then the gain margin is the gain at that point. And this is the explanation about gain margin. I will show in a diagram, will be easier. Okay, phase margin. Phase margin denoted by phase. This is in Greek, phase margin, phi, phase. Is obtained by looking into the frequency where the gain is 0 dB. So we look at 0 dB, and that gain, that frequency is called phase margin frequency, omega phi m, phase margin frequency. And the difference in between the phase value and 180 degrees is called phase margin, phase margin. Okay, perhaps not that apparent through this explanation. This is the one. Perhaps I'm sure easier to understand. Okay, again, our interest is 0 dB, always 0 dB, and minus 180 degrees. Okay, for the phase. We look into, sorry, this one should be 180 minus 180 degrees. This frequency is called omega GM, phase gain margin frequency. And when we look into gain, this value is called gain margin. My question is, the system stable? Is this system stable? Anyone?
Yes.
So this system is stable because at minus 180 degrees, the gain is negative. The magnitude is negative. So gain margin. Gain margin is this. Okay. And when for this example, where the system is stable, here gain margin is positive. Okay. Although this value, perhaps negative value, of course negative value below 0 dB, but when we say gain margin, we say gain margin here is positive. Okay. Please remember that many students make mistake. They just give the value negative, let's say negative 20 dB. No, it's 20 dB. When the system is stable. But if we have another system like this, magnitude, which is this is not stable, the gain margin is this. This is gain margin. But in this case, gain margin is negative. Okay? That is gain margin. When the system is stable, then we say positive gain margin. The otherwise unstable, negative gain margin. Then we have phase margin. How can we determine phase margin? Phase margin, first, we look into 0 dB. 0 dB, this is the point that they cross 0 dB, that the magnitude cross 0 dB. This is called omega phase margin. Okay, frequency, phase margin frequency. Phase margin frequency. And we look into the phase, and this is phase margin. The difference between this and 180 degrees. This is phase margin. Not this value. Not this value. Is the difference between 180 degrees and the phase here. That is phase margin. Okay, let's see one example. Consider a unity feedback system with this is the transfer function. So we have like this. GS inside. Find the gain margin and phase margin of the system. So how can we find gain margin and phase margin? First, to find gain margin, we look into 180 degrees, negative. This is the one. So here. And we look into the frequency. Frequency here is 1, 10, 2, 3, 4, 5, 6. 6 radian here, omega. So omega phase margin, omega gain margin is 6 radian per second. And this one also sometimes called phase crossover frequency. That means the frequency that cross 180 degrees. We call phase crossover frequency. Also omega GM. Then gain margin, we can look into here. This is gain margin. From here to here. Gain margin. Okay. This is the scale is small. This is actually here 5.5 dB. This is a stable system. Then gain margin is 5.5 dB. Any question here? We will do example with the from.
Doctor, I have a question.
From final year past year question with semi-log graph. Yes. Any
Doctor, I
question?
have question.
Yeah.
Um, the magnitude should be negative, right, doctor? Because the magnitude is below 0.
That's why I
It's
said
negative, right?
here, I mentioned already, okay, when the system
Okay.
is stable, this is a stable system, GM is below 0 dB. For gain margin, we say positive. Okay? Here, we say positive
Oh,
5.5. Although, yes, this is negative.
we don't write in negative, huh?
No. For stable
But
system,
we write in negative.
if I
Okay.
say gain margin minus 5.5, that means it's up here. 5.5 here. It's
Oh,
unstable.
it's wrong,
This
huh?
is unstable. Okay?
Stable.
Amirul, okay?
Okay, understand.
So please, many students, they give negative value. I think, of course, they took straight away from here, but please remember for positive, for a stable system, it must be positive. Right. So then we want to find phase margin. How to find phase margin? First, we look into 0 dB. This is 0 dB. And see here, this is the point. Okay, this is the point that it crossed 0 dB. And the frequency here, we call omega phase margin. Or sometimes also called gain crossover frequency. Why gain crossover frequency? Because this is the frequency that cross 0 dB. Okay, this is about 1, 2, 3, 4, 5. No. 1, 2, 3, 4.5. In between 4 and 5. So omega here about 4.5 radian per second. Okay, of course, when you read within certain range, we accept within certain range. So you go down here and see the angle here. Okay, take angle here. The angle here is about 147 degrees negative. Therefore, phase margin is 180 degrees minus 174 degrees. Because phase margin is the difference here. This is phase margin. The difference between 180 degrees and this angle. So about 23 degrees phase margin. Any question? How I know this? I actually refer to this.
No, not that.
This is actually given by MATLAB. Okay, this of course the accurate one. Gain margin 5.53 here, 5.53 at 6.16 radian per second. Here should be 6.16. Phase margin, phase margin 23.5 degrees, so 23.5 4.5 radian. Here per second, omega 4.51 radian per second. That is obtained, based on MATLAB. Of course, we will not obtain that. We would not be able to obtain until at that accuracy 0.1, 0.53. We can just estimate based on the graph given to us. All right. We will do more example here later, but gain margin and phase margin and stability are very important. They will be asked. Surely will be asked in the exam on the question on Bode plot. So far, we discussed Bode plot. Bode plot is in frequency domain. Okay. And our system that we want to control, let's say robot, motor, process control, all in time. What we can see in time. If we plot system like this in time, then we can understand. There is an overshoot, there is settling time, error. This is because this is the one that we can see. Okay. Frequency domain, of course, in abstract is an abstract one. Okay. Is used for design, is used for analysis. So there must be relationship between frequency domain and time domain. Otherwise, it will be no use of frequency domain. Because the real one, the actual one is in time domain. Okay. So in textbook, people were given the textbook, they show the relationship between frequency domain and time domain. Because later when we want to design, we mention in time domain normally. Let's say I want overshoot 10%, I want error this, I want settling time 1 second. All mentioned in time domain. So there must be relationship. There must be a relationship between time and frequency domain. And this is one of the relationship. Relationship between phase margin and damping ratio. This is a formula showing relationship between phase margin and damping ratio. Quite complicated controller. Formula. You do not have to memorize this. This equation is plotted here. Phase margin versus damping ratio. Okay. So we can see that if we increase phase margin, overshoot also, damping ratio also increase. Or I can say the other. If I increase damping ratio, phase margin also increase, but they are not linear. Okay, so this graph will be given in the exam. So when we say we want damping ratio 0.5, so then you can use 0.5 here. You know what phase margin required in order to get 0.5 damping ratio. we know that there is also relationship between overshoot and damping ratio. Overshoot and damping ratio are inversely proportional. If I increase damping ratio, overshoot reduce. If I use a low damping ratio, overshoot is high. So that means if I want less overshoot meaning here, about here, less overshoot mean high zeta. High zeta mean phase margin also must be high. Okay, so I conclude here, to have less overshoot, increase phase margin. Overshoot and zeta is inversely proportional. Phase margin and zeta, they are proportional but not linear. So if we want less overshoot, then we need to increase the phase margin. So here from this slide, we know that there is a relationship between phase margin and zeta and also overshoot. This will be later used for design. Okay, that is the first one. Second one, relationship between time response. Because in time response, we have all the time. We have a time to show the speed of the response. We have like settling time. Normally put TS, we have peak time. EP, we have also rise time. TR, we also have time constant. Time constant normally for a first order system. These times show the speed, demonstrate the speed of the response. And of course, we want a higher speed. We want a system, a response with high speed. That means a low settling time, low peak time, low rise time. This is the relationship between Bode plot and time, all this time. Okay. In Bode plot, we have what we call bandwidth. I will not go detail into this. Bandwidth is obtained by plotting closed loop Bode plot. The one that we normally plot is an open loop, but this is closed loop. And if we take minus 3 dB, here, this is called bandwidth. Okay. So the graph here show bandwidth, omega bandwidth. Bandwidth here, omega bandwidth, this is bandwidth, multiply with TS versus damping ratio, all versus damping ratio. This is omega bandwidth, multiply with TP. This is bandwidth, multiply with TS. Okay. Again, you do not have to if we ask, we will give the graph. So, to increase the speed of the response, the bandwidth should be increased. Because you see that, let's say I take settling time is TS versus is proportional to damping ratio. So if we maintain damping ratio, TS is zeta over omega bandwidth. And if we reduce, if we increase bandwidth, then TL will reduce. This is what we want. So to increase the speed of response, the bandwidth should be increased. So we want to have a system with high bandwidth. A high bandwidth meaning that the speed is increased, high speed. Okay, let's move. This is another one. We have just now about damping ratio and also overshoot. Then we have speed. Now error. The relationship between Bode plot and error versus error. Okay, remember that error is 1 over 1 plus Kp. I mentioned earlier about Kp, Kv, Ka, Kp, Kv, Ka, which is called static error constant. And error is equal to 1 over Kv or 1 over Ka. This is for step input. This is for ramp input. And finally, this is for parabolic input. Remember that the error is depending on the input. Okay, when we have system type 0 means s to power of 0 at the denominator. We will have system like this. The Bode plot magnitude will start by a straight line here, constant. Always like this. It's system type 0. And the value here, if we take value here, the value is 20 log Kp. So then we can find anti-log to obtain Kp. Once we obtain Kp, we can solve for the error. ESS 1 over 1 plus Kp. Next, for system type 1 meaning we have s to power of 1 here. The magnitude always start with minus 20 dB per decade. Here. Why? Because of S. Remember S here is like this. At 1, 20 dB per decade. If we make a line straight to 0 dB, this is 0 dB. This value here, the omega that we obtain here is Kv. And error is 1 over Kv. That means we can obtain Kp, we can obtain Kv directly from the Bode plot. Finally, system type 2. System type 2 will start with a magnitude with minus 40 dB per decade. We got s to power of 2. 1 over s2 and so on. So s power of 2 will give minus 40 dB per decade. And if you make a line to 0 dB, this is 0 dB, the value here is square root Ka. We can, in order to get Ka, we can square. Then we can solve for for the error. Okay, let's see example. Okay, before that, I want to say that of course, what we want is to reduce error. We want less error. How can we reduce error? if we can reduce error if we can increase all the static error constant for 1 over. So if increase, then error reduce. How to increase is by what we call increase magnitude at a lower frequency. This part is considered a lower frequency region. Then if we can increase the magnitude, then K, Kp, Kv, Ka will also be increased. Thus, error can be reduced. Let's see one example, a few examples on finding error. Find the steady state error based on this box plot. This box plot, this is the magnitude. If you see a box plot and it starts like this, 0, what we call slope, 0 slope, a straight line. This is surely system type 0 because it starts with this. And this value is 20 log Kp. Then we can find Kp. Uh, 20 log Kp equal to 25. Then we can solve for Kp. Kp I calculated is 17.78. Then you can find error. Error is 1 over 1 plus Kp. 1 plus 1 over 1 plus 17.78. Okay, that is error for system type 1, type 0. Any question?
No, Doctor.
Okay, next is another system. Now, the first one, it starts with 0 slope. Now it starts with a slope here, minus 20 dB per decade. You can see the slope by looking into 1 decade, how it go, how much different in 1 decade. And if the system, the magnitude, start with minus 20 dB per decade, this is surely system type 1. You can sure of that because the transfer function start with 1 s to the power of 1. S to the power of 1 will give a line, a straight line minus 20 dB per decade. If you make the line straight, not that apparent here, to 0 dB, like this one crossing 0 dB crossing here is the KV. Okay, KV here is 0.55. Here 0.2, 0.3, 0.4, 0.5, 0.6 here. Okay, the actual one 0.455 kV. Maybe if you use your graph become 0.6. So kV 0.55, then we can find error. Error 1 over kV. That is system type 1. Finally, we also have another example. In this, it starts with minus 40 dB per decade slope. You can see 1 decade here. 1 decade, 60, 60 minus 20, 40. So 1 decade, 40 dB. So this is a slope, a straight line with slope minus 40 dB per decade. So if you have a magnitude like this is a type 2 system. And if we make a line towards 0 dB, we want to find the 0 dB crossing. This value here is square root Ka. This is 1, 2, 3. Square root Ka equal to 3. So Ka equal to 9. Okay? And error is 1 over Ka. 1 over 9. Therefore, we can calculate error directly from the dot plot. Kp by finding Kp, Kv, and Ka. So the important message today is dot plot can be related. There is a relationship between dot plot in frequency domain and also specification in time domain. These are important in order to design a controller and also for analysis. Okay, finally today, I want to share with you aims for control in frequency response. What we want in order to obtain a good system. First, we want a stable system. That means we want at 180 degrees gain less than 0 dB. That's what we want, a stable system. This is number one. Number two, we want to increase phase margin, because by increasing phase margin, we can reduce overshoot. You can see the relationship, these two are inversely proportional. Increase phase margin, reduce overshoot. Number three, because we want to increase the speed, we have to increase the bandwidth. Omega, we have to increase bandwidth. And finally, number four, because we want to reduce error, we have to increase the magnitude at a lower frequency. Okay, because if we increase the magnitude at a lower frequency, then we will have higher Kp, Kv, and Ka. Higher Kp means less error. So these are four things to be done in control design using frequency response. I will stop here. In the next class, we will start using dot plot for design. I will take a few examples, a few past questions as an example, to show how can we design a controller. We will discuss 3 controllers. First, gain adjustment control. Number 2 is lag compensator. And number 3 is lead compensator. All these will be related to these 4 things. I'm preparing the assignment. I hope I can give to you by early next week. The assignment related to control design in time and frequency domain. I'm trying myself. I'm trying to design based on the control problem that we have here. Any question?
No, Doctor.
Next week we will start with gain adjustment, and we will have a test, right? Test will be on the 25th of May, next week.
Doctor, you said 28, right?
28 ke 26 25, I forgot.
Before puasa itu you said 28.
28 I will check.
Okay, thank you.
28 ke 25? 50. I will check, okay? And also I will inform you the one included. Surely chapter topic 1, topic 2, topic 3, which is frequency response. We actually are not sure whether to include or not. But if included is the one that we discussed until stability, until phase margin, gain margin.
Okay, Doctor.
Okay. You see, I will inform you. I give detail later by this week. I will find out today. Inform you. Okay, thank you very much. See you next.